As we start off Chapter 8, we're going to start looking at similar polygons. Chapter 8, we talk about similarities a lot. If you recall, we've talked about things being similar before a little bit, and the fact of dilations. And that's something that we'll be seeing a lot. If you remember dilations, how we dilated something to be larger and smaller. Those figures were similar, but they weren't exactly the same size. They were not congruent. They were just similar. So remember that similarity also, our symbol for similarity is just the one little squiggle line. There's no equal sign under it like congruency. It just means they're similar. So just like before when we looked at congruent polygons, we talked about like their corresponding parts. So in this section, the corresponding parts of similar polygons, we'll be looking at those as well. And remember, in similarity, like I said, similarity, they're the similar shape. They're not exactly the same size, but we basically multiply them by a scale factor. And that scale factor is usually represented by the letter K. And so like I said before, when we did dilations, we had a scale factor of K. And so when I go from this first triangle of ABC to triangle EF or DEF, each side length, so the side length originally of A, is multiplied by K to get KA. Okay, and it would give you a new side length. The angles in a shape and of course in a similar polygon is always going to be congruent. And so that's what it shows down here. Corresponding angles, they are congruent. And then the corresponding sides are going to be ratios. They're going to be similar. Okay, so ratios of the sides are proportional, is basically what this is telling us. Before we looked at proportions, proportional is just telling us that we can break it down, and where each of those ratios is going to be the same scale factor. It's going to equal our scale factor of K. So as we look at this example 1, it tells us that triangle RST is similar. Okay, there's that symbol already. Is similar to triangle XYZ. Okay, so that means the corresponding parts it's telling me are going to be similar. So if we first look at, it tells us find the scale factor. We're going to compare their sides. So if I look at the first two letters, I'm going to do RS and XY. I'm going to compare those two. So I'm going to have RS in comparison to XY. I can compare all the different sides, and they should give me all the same scale factors. So if I also do ST, the last two, would compare with YZ. So I do ST on top, YZ would be on the bottom. And then I'm going to connect my first and last one as well. So I would have RT is congruent with XZ. So I'm going to plug these in, and they should turn out to be equal. Since it's telling me that these are similar, all those sides should be proportional to each other if they are indeed similar figures. So if I plug them in, RS is 20. So I have 20 over XY is 12. ST, I have 30 over YZ, 18. RT is 25 over XZ of 15. So now I just want to reduce these. So 20 over 12, if I reduce both the top and the bottom, I can see both of them have factors of 4 in them. Then I would reduce the top down to 5 and the bottom down to 3. Sorry, I almost put 4. I was thinking 4. And the next one, 30 over 18, those both reduce by 6. So again, I would get 5 over 3. And the last one, they both are divisible by 5. They can reduce down to 5/3. So, since they all reduce to 5/3, that means this is my K. My scale factor, K, is equal to 5 over 3. That's my first answer for A. So if I were to look at this, and I looked from RST to ZXY, I want to know my scale factor to multiply them, so I would need to multiply something to get to the other one. Because in just doing our proportions, we got 5 over 3, but it's important to go back and check to see the order that it told you to do it. So it says RST 2XYZ. Well, notice they're getting smaller. If they're getting smaller, that means my scale factor has to be less than 1. So multiplying by 5/3 would actually be going the other direction. This would be multiplying by 5/3. So if I were to flip them over and I went going in reverse, this way is actually multiplying by 3/5. Okay, so my k, in this case, because we're going from RST to XYZ, it gets smaller, I'm actually going to flip it over to be 3/5. Okay. 5/3, I could do it, but I have to go from the smaller to the larger. That would get me, make my shape bigger. And this is just something, like I said again, you need to check it. My second one, B, it tells us that all pairs, list all pairs at congruent angles. So we need to list all the ones that are the same. So we go back to our original statement. Corresponding parts are in the same exact position. So my first letter is R in the first position, and so is X. So R, angle R, would be congruent with angle X. And if I go to my second position, in both of them, angle S would be congruent with angle Y. And then my last position, angle T, would be congruent with angle Z. Okay, these are in the same position in order to make your congruency statements. And then C tells you to write the ratios of the corresponding side lengths in a statement of proportionality. We already did that. In this first statement here, this shows our side lengths in a statement of proportionality. As we move on, we're going to look more at corresponding lengths in our polygons. So like we said, they have a ratio. And with ratios, we can only set up as proportions. So in this example 2, we want to find the corresponding length. If I set up the proportions, I want to find the value of x. X is EF. So I'm going to first look at EF as the last two, so that means it corresponds with NP. So I'm going to compare EF over NP. And this would be equal to one of my other corresponding ratios. So if I do, let's do the first two, DE and MN. DE would be over MN. And then I'm going to plug them in. So EF is my X, NP is my 30, DE is 15, and MN is 18. All we did here is we set up our proportions, okay, finding our corresponding parts. And then once we set up this proportion, we can cross multiply or do bat in the ball or whatever way that you learned. My method is always I cross multiply it. So I would get x times 18, which gives me 18x. And then I have 30 times 15, which gives me 450. Then to get x by itself, all I do is divide by 18 on both sides. And so it gives me x is 25. So my value of x is 25. The length of EF would be 25. In this next problem, we're doing the same thing. It tells us we have these two triangles that are similar, and asks us to find the length of the altitude. The altitude is just like our height. So if we have two similar triangles, that means that their heights are going to be similar as well. So if we want to find PS, we could put it over the height of the other triangle, PY. And then again, we want to set up a proportion just like we did in the last one. So if we did PS, that's the triangle on the left, we need to pick another side of that triangle. So we could do like TR, we could do TS, one of the side lengths that we know. So let's do TR, let's just do the whole thing. So I would do TR in comparison to my other side, the whole length, which would be XY. And so now if we plug this in, PS's are unknown, so I can either leave it as PS or you can put an X in there, an unknown variable. PY I know is 20. TR is 6 and 6, and that gives me 12. And XY is 8 and 8, so it gives me 16. And then again, I just cross multiply. So I would have 16 times PS would equal 20 times. And then I need to divide by 16 to get PS by itself. And so I get that PS has a length of 15. As we continue to look at similarity, we're going to talk about perimeter. So when we have perimeters of similar polygons, their perimeters are going to be equal to the ratios as well. We're going to be able to multiply those perimeters by the same scale factor that the sides were multiplied by. So I want you to think about if I have these lengths of like A, B, C, D, and then over here we had K, A, K, B, just like in the picture at the beginning. If I wanted to find the perimeter, I would add them all up, right? So for KLMN, I would do A plus B plus C plus D would equal the perimeter. For the second one, I would do KA plus KB plus KC plus KD would equal the perimeter of my second shape. Whenever I have a variable that is multiplied by every single number, I can always pull it out. It's like the opposite of distributing. Think about distribution. Whenever I distribute inside parentheses, I multiply it by every single number. I can do the opposite and I can pull the same amount out. So in this one, I would do K times A plus B plus C plus D. So as you can see, if we look at it this way, just like this theorem is saying, my perimeter here, my original, is simply multiplied by the scale factor again. Okay, and that's just something that we need to be able to notice, because especially once we look at area, it changes a little bit. But my perimeter is simply multiplied by the same exact scale factor that the sides are multiplied by. So as we look at this example, we have a model of a pool. There it says that they're going to have an Olympic pool, for one, has a length of 50 and a width of 25. So if L equals 50, the width equals 25. But the pool that they're building, they want the length to be 40 instead. And so we want to find the perimeter of the original, of the Olympic pool, and the perimeter of the new pool. So like if we put new on these ones and O's over here. Okay, so first we need to think about what the proportion is whenever we go from the Olympic pool to the new pool. So we're going to compare these. If I do the length of the new over the length of the Olympic, I would have 40 over 50, which converts down to 4/5. So that's going to be my K. 4/5 from the Olympic pool to the new pool. I multiply by 4/5. So if we think about the perimeter of the Olympic, which this is the picture they give us, we know that across from it it's going to be the same length. So all I have to do is add these all up for my perimeter. So 50 plus 50 gives me 100. 25 plus 25 gives me 50. So my perimeter of this one's going to be 150. I don't need to find my width of my new pool. Okay, they don't ask for that. They simply ask for the perimeter. Okay, so I have my perimeter of my Olympic. I know my scale factor now. So all I'm going to do is I'm going to do just like we could have done with the length. Once we found that 50 times 4/5 would give us 40, now we're going to do our 150 times 4/5 to give us our new perimeter. So when I multiply in fractions, I can multiply across the top. So I'm going to do my 150 times 4 gives me 600. And then I still have the 5 in the denominator. So then I can simplify that. So 600 divided by 5 is going to give me 120. So my original, or my Olympic original one that they looked at, my perimeter is 150. My perimeter of my new pool is 120. As we look at the next theorem, it talks about area. We're going to look at this the same way like we did the last one, but I'm just going to draw us like a rectangle. Okay, so if we have rectangle 1, call it 1, and we have rectangle 2, and we're going to say that they're similar to each other. If I look at my side lengths of A, B, C, D, or we'll just give it a width and a height, actually, of A and B, and then we have K times A and K times B, right? We multiply by the same scale factor to get our second one. So think about how we find area of a rectangle. We find area by doing length times width, or base times height. So my area of 1 would equal A times B, right? My area of 2 would equal KA times KB. Well, when I multiply variables, I can combine like variables, because this is just K times A times K times B. Okay, all of them are being multiplied together. So I would essentially be able to do just A times B for 1. And then I have 2K's, so I have to do K squared. Okay, so notice that this is different. This isn't like the perimeter one when we just multiply by the same scale factor. Now we multiply by that scale factor squared. Okay, think about what we put area, what their label is. Okay, whenever we do like perimeter, we can just do inches. But when we do area, we have to do inches squared or meters squared or centimeters squared. We have to have that square on there. The scale factor is affected the same way. So we have the square on our scale factor. So when we look at this example, we have that ABC is similar to DEF, and it wants us to find the area of DEF. Well, if you notice DEF, I don't have the height, and I don't have my base. I mean, even if I turned my triangle and I made 5 centimeters my base, I don't have a way to find the height. Okay, so I don't have a way to actually solve for my area. So we have to use the fact that they are similar figures. So first we need to compare them. Okay, whenever I go to DEF, so I'm going to have DE over its corresponding side of AB, which they gave us as well. So DE over AB, I have 5 over 10, which reduces down to 1/2. This is going to be my K. Then we said that we have the area of ABC. It tells us it's 36. We said we multiply area, if you go back, what I just said, we multiply area by K squared. Okay, so my area of DEF is going to equal 36 times my K squared. Okay, which in this case, 1/2 was my K, so I'm going to do 36 times 1/2 squared. When I square 1/2, I square the top and the bottom, so 1 squared is still 1. But 2 squared is 4, so I get times 1/4. And so 36 times 1/4, if I multiply the top, I get 36 over 4. 36 divided by 4 gives me 9. Okay, so if I put my label back on it, my area of DEF would equal 9 centimeters squared.